Have you ever, plugged in your phone charger or maybe flipped on a light switch or even just looked up at the power lines crisscrossing your neighborhood and thought, okay, how does this invisible force, electricity, actually get into my house?
Yeah, it's funny, isn't it?
It is. It's something we rely on, absolutely every single day. It powers everything, right? From morning coffee to watching TV at night. But for most of us, how it works, the mechanics behind it, that's still kind of a mystery, a black box.
It really is. We know what it does, definitely.
But the how? Yeah, that feels just out of reach sometimes.
You've hit on something really important there. The whole world of electricity, with currents, voltages, all these systems, it can seem really intimidating.
Good for sure.
It's just full of technical terms, jargon.
Yeah.
It feels like it belongs in engineering textbooks, not, everyday conversation.
Right.
And that perception, it can be a real barrier for people wanting to understand it.
And that's exactly why we're doing this deep dive. It's specifically for you, our curious listener. We get it. You want to grasp the basics, really understand what powers your life, but without getting totally snowed under by complex stuff or equations. So our mission today is pretty straightforward. We want to demystify one of electricity's really fundamental ideas, phase. We're going to tackle this totally from a beginner's point of view, make it clear, relatable, understandable.
Kind of like a shortcut, maybe?
Exactly. Think of it as taking a shortcut to being genuinely clued in about the electricity flowing through your home right now.
And we've got a great starting point for this. The material we're drawing on today comes from this fantastic book, Jeijin Shobo Joryuma Jungi.
Which translates to something like,
roughly, True Beginner's First Steps in Electricity. It's by Jen Byung-chil, published by Gilbert. And it's specifically written for people just starting out.
Perfect.
Yeah, so it gives us a really solid, accessible, and quite intuitive foundation for our chat today.
Okay, fantastic. So let's unpack this concept then. Phase. When we talk about electricity, especially the AC, the alternating current that comes out of your wall sockets, this term phase gets thrown around quite a bit.
It does.
It sounds technical, maybe a bit abstract, but what is it exactly? And maybe more to the point, why does it matter? Why should you, listening right now, care about phase when it comes to your lights, your fridge, whatever you plug in? Let's dive in.
Let's do it.
All right, now here's where it gets, really interesting right off the bat. Our source material, this beginner's guide, it doesn't jump straight into like Ohm's law or circuit diagrams.
No, it takes a different approach.
It really does. It starts with a concept that, many of us might recognize, but definitely not from science class. It brings up kwansang,
Which is?
physiognomy, the old Korean art of reading faces to predict someone's destiny or character.
Ah, right. I see where this is going.
Yeah.
It's a surprisingly clever way to ease into something technical, isn't it?
Totally unexpected.
Yeah, so in Gwansanghak physiognomy, that term Kong, pronounced song, it specifically means a person's appearance or their state.
Oh, yeah.
It's about looking at facial features, maybe their overall build, and figuring out things like personality, lifespan, maybe even wealth or fate. So at its core, it's about identifying a specific condition or a form or a characteristic.
Grounding it in something we can sort of picture.
Exactly. It makes the abstract a bit more relatable before we even get to the science.
So if in that cultural sense means state or condition, how on earth do we take that kind of broad idea and apply it to physics and then eventually to electricity? Seems like a big leap from reading faces to power grids.
Well, what's really fascinating is how the word phase itself already carries that broader meaning of state or condition even before we talk about electricity.
Okay.
In physics, when scientists talk about phase, they mean a distinct state of matter or maybe a specific condition of a whole system. Think of it like the different forms one substance can take, but it's still fundamentally the same stuff. So this immediately brings up a key question for us. How does this very general idea of state or condition map onto the world of electric currents?
Okay, give us some examples from physics then, the kind we might know, but maybe some others too.
Sure. Well, the ones everyone learns in school are solid, liquid, and gas. Right. So ice is the solid phase of water.
Right.
Liquid water is the liquid phase. Steam is the gaseous phase. Pretty straightforward. But physics takes this idea way further. For example, there's plasma. That's like a super hot ionized gas. You find it in stars, lightning, even inside neon signs. That's a distinct phase.
Okay, plasma. What else?
Then you've got liquid crystals. They're fascinating, used in loads of our screens like TVs and phones. They behave a bit like liquids and a bit like solid crystals. Another unique phase.
LCDs. Liquid crystal displays.
Exactly. And even something like a simple magnet can be talked about in terms of its magnetic phase, meaning a specific state where all its tiny internal magnetic bits are lined up.
So it's not just about whether something's solid or runny. It's about its fundamental state, its behavior, how its parts are arranged at that moment.
Precisely. It defines its specific condition. And the source actually gives a really simple but quite helpful example.
Oh, yeah.
Imagine a regular can of soda, just a normal beverage can. Inside that one can, you've clearly got liquid soda, right?
Yeah.
But you also have gas, the carbon dioxide bubbles. So even though it's just one can, one system, it's holding two distinct phases at the same time. The liquid phase and the gas phase.
Ah, okay. That makes it clear. One container, two states.
Yeah, it shows a single system can definitely have multiple phases coexisting.
That makes a lot more sense now. Okay, so we're taking this idea of a specific state or condition, and now we need to apply it to electricity, which is usually invisible. How does phase show up in an actual electrical system?
Right, so in electricity, and specifically when we're dealing with alternating current, AC, that's the key type here, phase gets a very precise meaning. It's all about the waveform of that current.
Waveform, like a wave in the ocean, crests and troughs.
Sort of like that, yes. But an electrical wave. Phase describes the timing, the sequence, and the relationship between these electrical waves as they move through a circuit. It's basically telling you where you are at any given point in time on the repeating cycle of that electrical wave.
Okay, so it's about the rhythm and timing of these invisible electrical waves. Let's start with the basics then, the kind of electricity we all have at home. Single-phase power. How is that even made? What's the beginner's guide to generating it?
Yeah, to really get single phase, picturing a simple generator helps a lot. Think of it as a basic machine that turns mechanical energy, something spinning, into electrical energy.
Okay, energy conversion.
Exactly. And at its heart, it's got two main parts working together.
All right, lay them on us. What are the key ingredients?
First, you need magnets. The source calls them kadada gaya. These create a steady magnetic field. That field is crucial. It's like the invisible stage where the action happens.
Got it. Magnets creating a field. What's next?
Then inside that field, you have the armature, or jungija. This is basically a coil of wire, a conductor, designed to spin around and around within that magnetic field. Picture a loop of wire just rotating constantly.
Okay, so a steady magnetic field and a coil of wire spinning inside it. What happens then? Where's the electricity come from?
Well, as that armature spins, the wires in the coil cut through the invisible lines of the magnetic field.
Cutting the field lines.
Right. And it's that action a conductor moving through or cutting magnetic field lines that induces an electric current in the wire. It generates electricity. This is the core principle. Electromagnetic induction discovered by Faraday. You're turning motion into electron flow.
Okay, makes sense. Spin faster or use stronger magnets, get more electricity.
Generally, yes.
Yeah.
But there's a practical problem. If this armature is just spinning and spinning, wouldn't the wires taking the power out get all twisted up?
Yeah. Like winding up a string until it breaks. How do you get the electricity out without everything getting tangled?
That's where a really clever little invention comes in.
Mm.
Slip rings.
Slip
Ring in Korean.
Slip rings.
Yeah, imagine two smooth metal rings attached to the spinning armature, each connected to one end of the wire coil. Then you have stationary brushes, usually made of carbon, that just gently press against these rotating rings.
Okay.
So the rings spin with the armature, but the brushes stay still, always touching the rings. This lets the electricity flow from the spinning coil through the rings to the brushes and then out to the external circuit continuously.
So the connection is maintained, but nothing gets twisted. That's clever.
It's a really neat solution. Allows continuous power extraction while everything's spinning.
Okay, so thanks to these slip rings stopping a wire catastrophe, we've got power coming out of our spinning generator. Now, the big question. What does that power actually look like electrically? What's its waveform?
Well, remember, as the armature spins through the magnetic field, the direction the current flows in its wires keeps changing. It reverses back and forth regularly.
Right, it's alternating.
Exactly. Our source uses a nice visual. Think of the current direction, switching from, say, red to blue, then back from blue to red over and over again. This constant reversal is what makes it AC, alternating current.
Okay, so the direction flips, but you said earlier that if we look at the output, we see just one waveform. How does that work if it's flipping back and forth?
Good question. Even though the direction of flow reverses, If you measure the voltage between the two output wires over time, maybe with an oscilloscope, you see a single, continuous repeating pattern.
Like that ocean wave again.
Very much like that. The voltage smoothly rises to a positive peak, falls back through zero, goes down to a negative peak, and then comes back up to zero to complete one full cycle. It's this single, repeating, undulating wave shape that defines single phase, we're saying. One complete electrical wave or cycle.
Okay, one smooth repeating wave. So what does that actually mean for us, at home? We've got this single wave of electricity. How relevant is this to, well, right now?
Oh, it's incredibly relevant. Single-phase electricity is, by far, the most common way power is delivered to our homes. When you think about the wiring in your house, or just look at a standard plug, you're dealing with a single-phase system. It's the residential standard.
Okay, so when I plug in my lamp, I see the two prongs on the plug. They go into the two holes in the outlet. That's the two-wire system for single phase.
That's it, exactly. Your home's electrical supply uses that two-wire connection. Plugging something in completes the circuit using those two wires. But here's an interesting point the source makes.
Yeah.
It says that while there are two wires, actually only one of them does the work in terms of carrying the fluctuating power to the device.
Okay. Two wires, but one's the main power carrier. What are these wires called and what do they each do?
Right, they have distinct names and jobs. One is the hot wire. You might also hear it called the power line or line wire. In Korean, oja, joli axian, or java songzian. This is the wire carrying the fluctuating voltage, like maybe 112 EV here in the US or 220 V in Korea. Its potential is constantly going high and low relative to the other wire. It's the live one, the one delivering the push.
Okay, the hot wire delivers the power. What about the second wire?
The second wire is the neutral wire, or zhangjian. This one provides the essential return path for the current, completing the circuit back to the source. And like its name suggests, it's meant to be electrically neutral, basically staying close to 0 volts relative to the ground. It's the stable reference point.
Hot wire brings the power, neutral wire takes it back.
Got it. So how does the electricity actually flow then? Does it just go from hot to neutral?
Well, because it's AC, it's not quite that simple. It's bidirectional. When the hot wire's potential is higher than the neutral's, yes, current flows from hot through your lamp to the neutral.
But then, as the AC cycle reverses, the hot wire's potential drops below the neutral's. At that point, the current actually flows the other way from the neutral through the lamp and back to the hot wire. It's this constant back and forth that powers AC devices.
Ah, okay, so it's oscillating, flowing both ways through the lamp. Definitely not like a battery. Okay, this brings us to something super common. Flipping a light switch. How does that fit into this hot-neutral, single-phase picture, and why are there rules about it?
Right, a light switch is basically just an intentional break in the circuit. You flip it, you open the circuit, electricity stops flowing, light goes off, flip it back, close the circuit, light comes on.
Simple enough.
But here's where a really, really critical safety point comes in, something the source emphasizes strongly. It's not just about breaking a wire. You have to break the right wire.
A critical safety point. Okay, this sounds important for everyone. What is it?
Yes, absolutely vital. The switch, whether it's for a light, an outlet, whatever, must be connected in the hot wire. The power line, the R-high, never ever in the neutral wire.
Okay, switch goes on the hot wire. Why is that so important? Why not the neutral? What's the risk?
It's all about safety when the switch is off. If the switch is correctly on the hot wire, flipping it off cuts the connection to the live voltage source. It completely de-energizes the circuit going to the light fixture.
So the light bulb socket is dead.
Exactly. There's no live voltage there, making it safe to touch, safe to change the bulb. The circuit is truly dead at the appliance.
Okay, that makes sense. So
Yeah.
what happens if someone wires it wrong, puts the switch on the neutral wire instead?
Ah, that's dangerous. If the switch is on the neutral wire, even when you turn it off, the hot wire is still directly connected to the appliance. The live voltage is still present at the light fixture.
Whoa!
Yeah. The switch has only broken the return path, not the path from the power source. So if you were to touch the fixture or its wiring, thinking it's off,
You could get shocked.
you absolutely could. Because there's still a dangerous potential difference, that electrical pressure we talked about between the live fixture and the ground you're standing on. Touching it could complete the circuit through you.
Wow. Okay, so that potential difference is the key. Even if the switch seems off, if it's on the neutral, the pressure is still there at the light.
Precisely. Think of it like closing a valve on the drain pipe of a full sink, neutral switch. Instead of closing the valve on the faucet filling the sink, hot switch, the water pressure is still present in the sink itself. Cutting the hot wire removes that pressure from the device entirely.
Okay, connecting this back to the bigger picture then. That detail about wiring a switch correctly isn't just a technicality for electricians. It's a fundamental safety rule for everyone.
Mm.
It shows why understanding which wire is hot and which is neutral is just so important.
Absolutely. It's basic electrical safety 101.
Yeah.
Proper wiring ensures that off really means safe. It minimizes the risk of shock, which is paramount. It gives you peace of mind when you're doing something as simple as changing a bulb.
So single phase is basically tailor-made for our homes. It's efficient enough, safe if you follow the rules, and cost-effective for what we need.
Is that the main reason we don't usually see other types like, say, three-phase power in a typical house?
That's exactly it. Most things in our homes, lights, TVs, computers, kitchen appliances, small motors in fans or blenders, they just don't draw huge amounts of power. They're considered small loads.
Right.
And for these small loads, single phase is way more economical. The wiring's simpler, requires fewer conductors, the circuit breakers and outlets are less complex and cheaper. The whole infrastructure for residential single phase is just more straightforward and cost-effective.
It just fits the need perfectly.
Yeah, it's optimized for residential use. There's usually no real benefit that would justify the extra cost and complexity of bringing a heavier duty system like three-phase into a standard home. It wouldn't strain the power supply for our usual gadgets anyway. Okay, so single phase is our home champion. But we do hear about three-phase power, usually for big stuff, right? Factories, industrial sites, maybe large office buildings. What exactly is three-phase, and how different is it from our single-phase wave? Is it just 3 times the power?
It's a bit more nuanced than just 3 times the power, but yes, it's fundamentally different and much more suited for heavy-duty applications. Unlike single-phase with its one waveform, three-phase power involves, well, 3 distinct electrical waveforms working together.
Okay, 3 waves instead of 1.
Right. Imagine you have 3 separate single-phase sources, but instead of being random, they're perfectly synchronized and combined in a very specific way. That synchronization is key.
Synchronized how? Is there a special timing between these 3 waves?
Absolutely. And this is the core feature that makes three-phase so powerful and efficient. The 3 individual waveforms are precisely offset from each other in time. Specifically, they're 120 degrees out of phase with each other.
120 degrees, like dividing a circle into 3 equal parts?
Exactly like that. If you graph them, one wave starts its cycle. Then, 1/3 of a cycle later, that's 120 degrees, the second wave starts. Then, another third of a cycle later, the third wave starts. If you picture a clock face, maybe wave 1 peaks at 12, wave 2 peaks at 4, and wave 3 peaks at 8.
Huh. What's fascinating there is how just by adding 2 more waves and staggering them like that, 120 degrees apart, you get a totally different kind of power. Makes you wonder why we don't just use that everywhere.
Well, that careful staggering is precisely its genius. Unlike single phase, where the power level naturally dips up and down, even hitting 0 twice per cycle.
Right, the wave goes up and down.
With three-phase, the power delivery is much more constant, much smoother. Because the peaks are staggered, at any given moment, at least one of the phases is delivering significant power. The total power output never drops to 0.
Ah, okay, so it's like having 3 pistons firing in sequence in an engine rather than just one. Smoother power.
That's a great analogy. Yes, it provides a much more continuous, uninterrupted flow of energy, and that's why it's ideal for heavy industrial loads. Think about massive motors in a factory, or big pumps or elevators.
Yeah, they need constant power.
Exactly. If their power fluctuated like single phase, the motors wouldn't run smoothly, they'd vibrate more, be less efficient, and might even wear out faster. Three-phase gives them that smooth, constant torque they need to operate efficiently and reliably. It's the gold standard for industry. Large motors, data centers, anything needing stable, heavy power.
Makes sense. Reliability is key there. How is it generated? Is it just 3 single-phase generators hooked together somehow?
You could think of it that way conceptually, but a dedicated three-phase generator, or alternator, is designed specifically for it. Instead of just one rotating coil, it typically has 3 separate sets of stationary coils called windings.
Okay, 3 sets of coils.
Right, and these windings are physically arranged 120 degrees apart around the inside of the generator. Then, a central magnet rotates inside. As the magnet spins, its field cuts across each set of windings in sequence, inducing a separate AC current in each one.
And because the coils are 120 degrees apart.
The currents generated in them are automatically 120 degrees out of phase with each other. It's a really elegant design that produces those 3 synchronized waves simultaneously.
Very neat. Okay, so if three-phase is so good, so efficient, so smooth, why isn't it standard for homes? The source specifically says it's rare in general households.
Yeah, the main reason goes right back to what we said about home appliances. They just don't need that kind of heavy-duty constant power delivery. The small loads in our homes are perfectly happy with single phase,
So it's overkill.
pretty much.
Yeah.
And it's significantly more expensive to implement. You need more complex wiring, usually 3 or 4 wires instead of 2, more complex circuit breakers, outlets, plugs.
Yep.
And the appliances themselves would need to be designed for 3-phase, making them more expensive too.
Right.
So for residential use, the extra cost and complexity just aren't justified by any real performance benefit for typical home devices. Single phase is the economical and practical choice.
And there's probably a standardization aspect too, right? Easier to just have two main systems.
You're absolutely right. The source hints at this. Having too many different electrical systems would be a nightmare. Think about it. Power plants, transmission lines, substations, building wiring, appliance manufacturing. Everything needs to be compatible.
Yeah, it'd be chaos.
Exactly. So single phase for residential and light commercial and 3-phase for industrial and heavy commercial have become the dominant global standards. They cover almost all the bases efficiently. It simplifies everything from engineering to manufacturing to maintenance.
Okay, that makes sense. But then the source makes this really interesting little connection. It says single-phase power can actually be seen as part of a three-phase system. That kind of makes me wonder, even though my house runs on single-phase, did that power start as something bigger and more complex?
That's a fantastic insight, and yes, it points to how our whole electrical grid is interconnected. If we zoom out and look at the bigger picture, that simple single-wave electricity coming into your home, more often than not, it was originally part of a larger 3-phase system.
Really? So those huge power lines you see marching across the countryside, they're carrying three-phase?
Overwhelmingly, yes.
Yeah.
For transmitting power over long distances from the generating station, maybe hundreds of miles away, to your local town substation 3-phase is way more efficient.
Why is that?
It can deliver more power using less conductor material, fewer or smaller wires, compared to sending the same amount of power via single phase. This saves a huge amount on copper or aluminum for the lines, and also reduces energy losses during transmission. So 3-phase is the backbone, the highway system for bulk power transmission.
Okay, the highway.
And then, when that high-voltage 3-phase power reaches your local neighborhood substation, it gets transformed down to lower voltages. And for houses and smaller businesses, they typically just tap off one of those 3 phases, pairing it with a neutral wire to create the single-phase supply you use.
Ah, so it's like taking an off-ramp from the main power highway.
That's a perfect analogy. The utility essentially takes one lane of the 3-lane highway and directs it down your street. This shows the amazing scalability and flexibility of the system. Generate and transmit in bulk using efficient 3-phase, then distribute it locally as needed, often breaking it down into single-phase for end users.
So the single phase in my house is often just one piece of a bigger three-phase puzzle that started way back at the power plant.
That's often exactly how it works. It demonstrates how the system is designed for efficiency at every stage, from massive generation down to your phone charger. The key takeaway for you, listening, is that single phase is optimized for homes, convenient, cost-effective for smaller loads. 3-phase is the industrial powerhouse, driving heavy machinery efficiently. And very often, your home's power is ingeniously derived from that larger 3-phase grid.
Wow, okay. This has actually been really illuminating. We've gone from face reading to power grids, all starting with this idea of phase. Let's maybe just quickly recap the main things we've pulled out today.
Yeah, definitely. So we started by seeing phase not just as an electrical term, but as a general physics idea of a state or condition, like solid, liquid, gas, for water.
Right.
That helped build a bridge, right?
Right, made it less abstract. And then in electricity, specifically AC, phase is all about the timing and the shape, the waveform of the current. And the big difference we focused on was single phase versus 3-phase.
Exactly. Single phase. That's the one way, is the standard for our homes, delivered typically by 2 wires, the hot wire carrying the voltage, and the neutral wire providing the return path. It's cost-effective and great for the smaller electrical loads we usually have.
And that crucial safety point. Switches absolutely must go on the hot wire, not the neutral. Flipping the switch then truly de-energizes the appliance, making it safe. Cannot stress that enough.
So important and non-negotiable safety basic.
Yeah.
Then we looked at 3-phase power. That's the system with 3 ways, each offset by 120 degrees.
Right, the smoother, more constant power delivery.
Precisely. Which makes it super efficient and stable, ideal for big industrial motors and heavy machinery, but generally overkill and too expensive for a typical home.
And finally, that really cool connection, realizing that our home's single-phase power is often just tapped off from the larger three-phase grid that transmits power across the country, shows how cleverly designed the whole system is.
Yeah, it's all interconnected. So the main things for you, the listener, to take away are: phase describes the timing and wave shape of AC. Your home uses single phase, optimized for your needs. Safety with wiring, especially switches on the hot wire, is critical. And even your simple wall outlet connects you to a vast, complex, and pretty amazing electrical world.
Absolutely. So now that you understand a bit about phase, maybe pause and think about that huge power grid for a second. If the single phase in your home is often just one slice of a bigger three-phase pie, what other fascinating layers of electrical engineering might be hidden, behind your walls, under the streets, and those big transmission towers, all working silently, 247 to power everything?
Hmm.
Next time you plug something in or maybe see a factory humming away, just take a moment. Think about the different kinds of power they might be using. You might find you notice and appreciate this invisible infrastructure just a little bit more, all thanks to understanding this basic idea of phase.